Small presentation of the jury. So the jury will be composed by Benoit Marx from his associate professor from University Lorraine, Castillo Pedro, professor at the University Technology of Compiègne, UTC, and then Christina Manu, professor central supérieur at Université Paris-Saclay, myself from University Mohamed Jamaï, from University Polytechnique Hauts-de-France, and now I have to say INSA Hauts-de-France, and your supervisors, Professor Saïd Mamar at University Évry, and Professor Dalil Ishalel, University Évry. So Pham, you will have 45 minutes to make your presentation, and after that we will have some questions, a couple of questions from the jury, member of jury, and you will have the deliberation after that. So you can start, Pham.
Yes, thank you, Professor. So hello everybody, my name is Pham, and I am a PhD student under supervisors of Professor Said Mama and Professor Dalit Icholang at the IBISC laboratory, University Évry Val, University Paris-Saclay. First of all, I would like to express my greatest gratitude towards the late Professor Yasmina Bestawi, the teacher whom I respect enormously both professionally and personally. Her knowledge, passion, and kindness have always been a source of inspiration. Without her, this thesis could never have begun and could not have gotten this far. I would like to thank all the jury members, Professor Christina Manu, Professor Mohamed Jumair, Professor Pedro Castillo, and Professor Benoit Marx, who kindly accepted to be the jury members of my thesis defense. I also want to thank my directors of the thesis, Professor Said Mama and Professor Dalit Ichoran, for what they have done and helped me during the thesis term. Now I'm going to present my work, Robust Path Planning and Control of Unmanned Aerial Vehicles. My presentation contains 5 sections. In the first section, I will talk about the motivation objective. The second section will talk about the modeling of the quadcopter. The third and the fourth sections are the main sections of the thesis, and we'll talk about the path planning and control of quadcopter applied to the precision agriculture. In the last section, the conclusions and further researches of the thesis work will be discussed. Now let's move to the introduction. Human beings are facing huge challenges for sustainable food production. We have to produce more food while the agricultural areas is increasing. Many factors are affecting to agriculture, such as population changes, climate changes, water resources for agriculture are reducing seriously. Several methods have been applied to agriculture for improving the crop production. Precision agriculture is now very popular, where robots and information technologies are applied. Several types of robots, such as mobile robots, UAVs, or the combinations of them, are widely applied in precision agriculture. This picture shows several applications of UAV in precision agriculture, such as data acquisition, photography, pesticide spraying, and irrigation management. Now let's move to the motivation of the thesis. The UAV has to face several challenges when working in agriculture area. For example, the UAV has to visit on the predefined waypoint while avoiding obstacles and minimize some objective functions such as the energy, the trajectory length, or the working time due to the limitation of the battery power. Besides, when flights in the agriculture area, disturbances such as the wind or the changes of the dynamic parameters such as the mass or the moments of inertia or the measurement noises can affect to the control of the UAV to follow exactly the predefined trajectory. So we are motivated in this thesis by coverage, path planning scenario, and control of UAV in precision agriculture for detecting all the infected areas and pesticide spraying to all the infected areas. So the objective of this thesis is to realize the modeling, planning, and control of unmanned helicopters robot for monitoring large area in precision agriculture. So for the path planning objective, in pest surveillance mission, drones will be equipped with the specialized cameras in order to monitor the whole agriculture area. We need to capture images by specialized cameras, and then a trajectory will be researched and generated to enable the UV to capture the images of entire crop areas and avoid obstacles during the flight and minimize the path length. For the insecticide spraying task, a trajectory will be researched and generated to enable the UV to insecticide on over the infected area of crop. And when the UV working in the agriculture, so the mass might change during the time. So as the moments of inertia can be changed. So consequently, robust controller and observer have to be designed for the quadcopter to follow exactly the predefined trajectory while keep stabilizing the UV under the changes of dynamic parameters and the influence of external disturbances. Now we are going to the second section, quadcopter modeling. So in this section, I will talk about the quadcopter modeling. Quadcopter contains 4 rotors attached to a frame. The movement of the quadcopter is applied by appropriate adjusting the speed of the 4 rotors. There are 2 reference frames that are using for modeling the quadcopter: the earth fixed frame and the body fixed frame. The absolute position, the Euler angles, the velocity in the body fixed frame, and the angular velocity are these variables, and their relationship are depicted in the equation 1 and 2. And there are 3 types of forces that acted to the quadcopter: gravity, thrust, and hub forces. Gravity is the force by which a planet or as a body draw object toward its center, and gravity is along with the z-axis in the negative direction. And each rotor produces the thrust Ti and the hub force Hi, which are dependent on its angular velocity of the rotor. Once the main forces have been reviewed, the net external force vector acting on the vehicle is expressed in the body fixed frame as in the equation 3. The main external moments that are expressed in the body fixed frame are the rolling, pitching, yachting, the hub, the gyroscopic, and the blade flapping moments. The rolling and pitching moments are achieved by the difference in combined thrust in the opposite side of the vehicles. These moments are really important because they contribute to the control of the vehicle. The directions of these moments are decided according to the right-hand rules. Yachting moment Qi around the shaft of the eye rotor is generated by the acting of the aerodynamic forces on the blade elements. And there are several moments more like the blade flapping, the hub moments, the gyroscopic, and the blade flapping. For constructing the mathematical model of the quadcopter, we assume this assumption, and then we define the Lagrangian error is the summation of the translational and rotational energies minus potential energy as in 5 and 6. And now we take the derivative of the translational and rotational Lagrangian, and we can get the system differential equation of the quadcopter S in the equation 7. And the system differential equation of the quadcopter can be rewritten in the matrix form S in 8, where X is the state and U is the input of the system. So from the equation 7, we can see that the rotation subsystem of the quadcopter doesn't depend on the translational subsystem. However, the translational subsystem is dependent on the rotational subsystem, like in the figure 12. Now we are going to the third section, path planning. So in order to accomplish the predefined task, a trajectory for the quadcopter is required. In this section, we are going to study the trajectory generation for the quadcopter to accomplish the task infected area and the task pesticide spraying. So suppose we have an agricultural area like in figure 15, and the obstacles are the yellow polygons, the white areas where the plants are the areas where the plants are free of pest. The red dot here are the area where crops are infected. The coordinates of the obstacles are assumed to be known in priori, and the coordinates of the infected crop, the red dot, are not known in priori. So our main tasks are infected area detection and pesticide spraying. So for infected area detection, we have to detect the coordinates of all the infected area of crop by using UV, which is equipped with the specialized camera. It means that a trajectory have to be generated such that the entire agriculture area will be covered by the pictures that will be taken by the UV, and while moving, the UV has to avoid the obstacles, and it has to maximize also the infected area that the picture can cover, and minimize the path length for the UV to fly. For pesticide spraying, with the information about the coordinates of all the infected area, as we have already generated as in the first task, we have to spray the pesticide to all the infected area of crop by using the UV, which is equipped with the pesticide tank, and the UV also has to avoid the obstacle and minimize the path length, and the pesticide should be sprayed to all the infected area. So this is our proposed approach for infected area detection. So first, the agricultural area is divided to smaller regions by the cellular decomposition block. Then the waypoint generation block will generate the waypoint for each of these smaller regions. Next, we're going to optimize this waypoint by block optimization scanned area. The results will be compared with the trader function till we get the results. Finally, the path for the covering on the agriculture area will be generated by the block optimized path planning generation. Now let's see the cellular decomposition. So in the previous approach, they used the vertical line to swap from the left to the right to detect the critical point, like here and here, and then from the critical point they will draw the vertical line like here in order to split the environment to several cells. In our approach, we also use the vertical line to swap from the left to the right. However, in our approach, the critical points are categorized into much more groups, into 4 groups as following. And for each group of the critical points, we will have a specialized method in order to draw the horizontal line to divide the environment like here, and then this is the results for the same environment. We can see that in our approach we divide the environment to only 2 cells, smaller cells, compared to the 4 cells as the proposed approach. Now we see the simulation for a much complicated environment like this, like here. So based on our approach, the critical points will be detected as in figured, as in this figured, and then the environment will be divided to smaller cells as in figured 21, and we can see that the number of cells that we got is only 6 compared to more than 20 cells if we use the previous approach. So suppose that the picture frames of the camera that can be taken, that attached to the quadcopter, is in the rectangle form like this one. So for the purpose that we have to take the picture on the area, the picture frame should be taken such that the neighbor frame are overlapped like in the figure 23. Then the picture frame for all the environment should be taken as in the figure 24. And we can see that there are some pictures frames that the center do not belong to the octagons as in the figure 25. So you can see that on this picture frame don't belong to the octagons. Now the Bush-Chevron trajectory will be generated based on the picture frame in each cell as in the figure 26 like here. And for maximizing the percentage of the coverage, we have to adjust the coordinates of the picture frame. And in this simulation, when the simulation so for maximizing the percentage of the coverage, we have to adjust the coordinate of the picture, and we have to adjust only the first coordinate of the picture frame, and the others will be follow. And in this simulation, so we choose that the picture frame has this dimension, and we can see that the percentage of coverage can be up to 96.335%. And in the second simulation, when we decrease the size of picture frame, we can see that the percentage of coverage can be up to 97.8%. Now the Bush-Chevron trajectory for each cell has been generated. We can see that for each cells we have 2 points to get 1 point to get in and 1 point to get out. So now we have to find a trajectory for the UV to change between the cells. So for each cells we have for example, for this cell we have 1 point in or out, but we don't know which point will be the point for in, and which point will be the point for out. But if with the UV get in at the point 1A, it should take the Bush-Chevron inside the cell inside these cells and get out at the point 1b. So means that the traditional traveling serum miles problem cannot be applied. In this thesis, we add additional constraint like in 13 to make sure that if the UV get into the cell at 1A, it will get out of the cell at 1B, and the inverse. And we also apply the genetic algorithm with the traveling the TSP problem to make sure that the solution is always exist and decrease the processing time by focusing the swap, the flip, and the slide operations as in the figure 29. So the advantages of the proposed three operation flip, slide, and swap is that the search for the optimum path faster, because this search is performed only on a set of path that satisfies the given request, and the solution is always found even with the number of cells is huge. So this is the simulation. So if we don't use our approach, the solution cannot be found. And with our approach, we can find the solution with this time of processing for the computer. So, and this is the algorithm for the genetic algorithm and the DSP problem. And this is the simulation for getting the trajectory to change between the cells. So we have the cells with the in point and out point, and this is the result for changing between the cells. And now we're going to the pesticide spraying task. So this is the algorithm for the pesticide spraying. Based on the information about the map infected area and the obstacles, the infected area will be divided into smaller regions by the block map division. Then we will generate the waypoint for each these regions by the block waypoint infected area. Then we generate the trajectory for changing between the regions. So suppose we have this agriculture area, and by using the k-means clustering algorithm, we can divide the infected area to smaller cluster, like in the different colors of the dots in 34. And then we have to find the polygon to cover each of these regions. So we can use the two approach. The first one is the minimum convex polygon in order to cover on this point, and the second is the boundary cover polygon covers the infected point. And we can see that this polygon still have some part of the obstacles, and it means that our our drones cannot go through all of this one. So now we have to divide this polygons into smaller convex polygon as in this one in order to generate the most different trajectory. And we can see that the number of the small convex polygon for the boundary polygons are much more than the approach minimum convex polygon. However, the area of this approach is less than the area of this approach. So this is how we split the convex polygon to several polygons which have two parallel edges based on the angle. And this is the diagram for dividing the environment to obstacle-free convex polygons. Now we have to generate the most different trajectory for each smaller convex polygon that we have been generated, like this one. And each convex polygon can be split into several polygons which has two parallel edges, like this one, like the polygon A, B, C, D, E, F, G, like here. And we suppose that the UV can spray the pesticide inside the circle with the diameter 2r. So if the drone goes from P to M to N, so all the area of this polygon can be covered by the UV. So this is how we split the convex polygon to several polygons which have two parallel edges based on the angle alpha. And by adjusting this alpha, we can see which alpha will be the angle that the path length for this polygon will be convex polygon will be the minimum. And this is the simulation. This is the algorithm for finding the alpha angle. And so we adjust it from 0 to 179 degrees, and we find the path length, and then we can get the angle alpha. And this is the simulation for generating the burst difference for the UV in each smaller convex polygons like this one, and like in for both approaches. And this is the simulation for the whole bigger agriculture area. So now we are going to the next section, the control. So for the purpose of convenient control of the quadcopter, the controller of the quadcopter is divided into two loops, the inner loop and the outer loops, based on the fact that the translational subsystem is dependent on the rotational subsystem. However, the rotational subsystem does not depend on the translational system. And even for one more reasons that this will be simpler for designing the controller. So several controllers have been and observer have been proposed in the contents of the thesis. However, due to the limitation of the presentation time, so only some of them will be presented in this presentation. So now we are going to design the trajectory following controller for the quadcopter. So this controller contains three subcontrollers. The integral backstepping for the altitude of the controller. It means that this controller will control the height of the quadcopter, so the Z parameter, the Z state, and the PD controller will be for the position controller. So this controller will control the X and the Y, and the LPV H infinity output feedback controller for the altitude controller. So this controller will control the heading, roll, pitch, and yaw of the quadcopter. Now we are going to see the position controller. So the system differential equation of the dynamics for the position subsystem of the quadcopter can be given by in the equation 14. And now we are going to define the error of the position and velocity as in 15. And now we want this error to decay exponentially to 0. So we force this error to obey this second order linear differential equation with proper coefficients, like in 16, where x c dot dot and y c dot dot as command isolation, which are calculated by the controller, and then the desired phi and theta can be calculated as in 18, like here. And this is the coefficients for the PD controller that we have selected as in 19. So now the altitude controller. So the differential equation of dynamic altitude subsystem is given in 20, like this one. And now we are going to define the error of the altitude z, its derivative, and the integral, like in the equation 21. So now we will study the stability of the altitude system by using the Lyapunov function. So we will define the Lyapunov function v2 like in equation 22, and its derivative v2 dot as in 23. And now for ensuring that the v2 dot is always negative, we have to choose the u1 s in the equation 24, where the c5, c6, and lambda phi are the positive numbers. So based on this one, we can calculate that the V2 dot equal to minus C5 Z5 square minus C6 Z6 square, and C5 and C6 are the positive number. So we can make sure that the V2 dot is always negative, and the coefficient of the backstepping controller are selected as in 26. Now we are going to design the LPV H infinity attitude output feedback controller of the quadcopter, of the mass varying quadcopter. So in this, now we assume that the quadcopter is symmetric and the Ix equal to Iy. So the system differential equation of the rotation dynamic will be given in the equation 27. And one thing that the mass of the quadcopter is varying, so is the moments of inertia Ix, Iy, and Iz, because these moments of inertia are related to the mass, and we have also the omega r is the summation of the rotor speed are also changing. So now we are going to see the LPV H infinity output feedback controller for the round pitch system. So this is the system differential equation of the round pitch, which is rewritten in the descriptive form in order to decrease the number of varying parameters. And this is the descriptive form of the system, and this is the system matrix E, A, B, C, A, D, and E, and this is the varying parameter. And we can see that the first varying parameter is Ix, the second parameter depends on Ix, Iz, and C dot, and the third varying parameter are omega r. And we assume that all these parameters are measured or can be calculated or measured. So in order to express the system in the polytopic form, the system matrices A, B, C, D, and E can be expressed like in the equation 31. So, and for penalizing the output of the system, we also add the weight function like here WU1, U2, WP1, WP2. And now we can generate, and now our purpose is to design the controller. This is the output feedback controller for the round pitch subsystem, and phi reference and theta reference as the echogenous input, and this one as the echogenous output. And we can calculate the norm of the LPVH infinity round pitch subsystem as here we can calculate, and its value is 0.544. And the same procedure can be done for the yacht subsystem. So first we're going to rewrite the system yacht system in the descriptive form like in 34, and then the system matrices A, B, C, D, and we choose the varying parameter is the Iz, and then we express the system matrix A, B, C, D, and E in the polytopic form S35. And we choose also the weighting function WU3, WP3, and we can calculate the LPV H infinity controller KY with the norm of the system is 0.0188 like here. And now we are going to see the simulation results. So in this simulation, the mass changes gradually from 2 kg to 1.12 kg, and the moments of inertia Ix and Yz are also changing in this figure. And we also simulate another situation when the mass abruptly changing, like at 10, 30, 50, and 85 seconds, like in this equation, in this figure. And we define the disturbances as wind for X, Y, and Z in this figure. And we can see that the actual signal X, Y, and Z checks the desired signal well for both cases. Changing the mass gradually and abruptly. And in the figure 53, we can see the error signals of x, y, z related to the actuant and the error between the real and the, the reference signals, and we can see that the maximum error is about 0.15 mil, and this is the response of x, y, z in 2D and 3D. So this is the second scenario for the simulations. The same simulation is done, but in this simulation we change the type of this disturbances as in these figures, and we can see that the actuant signal x, y, and z also checks the desired signal, where for both cases of changing of mass. And these are the error signals for x, y, and z, and here are the responses of x, y, z, and z in 2D and 3D. So based on the fact that the dynamic coefficient of the quadcopter change can affect to the stabilization of the quadcopter, so now we are going to design the LPV H infinity state feedback controller for the altitude subsystem of the mass varying quadcopter. So the system differential equation of the rotational of the altitude subsystem can be depicted in 37, where d phi, d theta, d psi, and dz are the disturbance. So here we also take into account the dynamic of the actuator as in equation 38 and 39. So the system differential equation can be transformed to 40, like here, with we form the d. D is the disturbances. It contains d phi, d theta, d psi, d z, and g. Then the LPV model of the altitude subsystem of the quadcopter is performed as in 41, and we can see that the system matrices A, B, and E are the parameter dependent matrices based on Ix, Iz, omega R, and M. And we define the varying parameter S in 42. Then a 16 submarine Takahashi-Shiro system is achieved by 43. And for the purpose that the output of the system checks the reference R, we will define the extra state as in 46, and for penalizing the output, we define also the weighting function as in 48. And to get the Fi parameter dependent system, we define the exogenous input W, like here the exogenous output Z, and the augmented state, like here, and then the Fi parameter dependent system can be generated as 49, with the system matrices are here. So now the aim is to design the LPVH infinity optimal state feedback controller of the form 50, making the closed loop system 51 robustly asymptotically stable. So by solving the optimization defined in 52, this is the LMI's 52, the optimal state H infinity state feedback controller with the smallest attenuation level omega for the altitude subsystem of the mass varying quadcopter can be reformulated as in 53. And this is the simulation for the state feedback controller. So this is the case when the mass is abruptly changing, and so is the moments of inertia, and we define these are the disturbances, and we can see that the response of the system is pretty well. The actual value of phi, theta, psi, and z checks the reference well, even under the disturbances. And the same simulation can be done for in the second scenario. And due to the fact that there are a number of parameters that are really hard to measure or even impossible to measure or really expensive, we design the observer for the mass varying quadcopter. However, the dynamic parameters are changing as the mass moments of inertia. The observer with the fixed structure might not work working well. Consequently, here we propose the LPV unknown input observer for the altitude of the mass varying quadcopter. So suppose we want to design the LPV unknown input observer for the LPV system in 54, and we can see that this system contains the known input. So this system can be transformed to the new dynamics system in 57 without the known input by defining the auxiliary system like in 56. And suppose that the ith output has the relative degree or Ri, and now we take the derivative of the output y as in the equation 59, and we can rewrite it in the matrix form as in 60. So the proposed LPV unknown input observer has been proposed as in 61, and this where Q and R are the coefficient to be determined. So this is the theorem. So the system 61 is an observer for the system 57 if these conditions are satisfied. Now we are going to see the convergent analysis. So we define the derivative of the error of the state and the error of the disturbance in 62, and now we transform all the matrices in the polytopic form as in 63, and we can see that the gain matrix L rho can be expressed as also as in the polytopic form as in 65. And now we can calculate the z dot s in 66, and we define the Lyapunov function s in 67, and we calculate the derivative of this Lyapunov function. So in order to guarantee the negativity of the Lyapunov function, the term in the here should be always negative infinite, and this list lead to the sufficient LMI conditions for ensuring asymptotic stability of the system as in 70, and the gains Li can be obtained as in 71. And now we are going to see the designing of the LPV unknown input observer for the round pitch subsystem. So this is the differential equation of the round pitch system, and we transform this. We define the varying parameter. We transform it to the system without the known input, and we take the derivative of the output, and we see the relative degree as here. And then we define the LMIs, and we can calculate the observer gain L by solving the LMIs that we have already seen. And the same procedure can be applied for the Yost subsystem. We define the system without the known input, and we can calculate the Q, and then we define the LMIs and solving the LMIs, and we can get the observer gain error. And this is the simulation result. So for the first simulation, we don't consider the measurement noise. So in this simulation, the mass is gradually changed from 2 kg to 1.12 kg. And we can see in the figure 75 that the estimate unknown input dz, d5, d theta, and d psi converge to the actual value after maybe 5 seconds. And in the figure 76, you can see that the error of the estimation it's small and converges to 0. Now we are going to see another simulation result where we assume that the measurement noise exists. So so now and in this simulation the mass is abruptly changing. So we can see that in the figure 83 that the estimated unknown converts to the real value well after 5 seconds, and in the equation 50 in the figure 84 we can see that the error of the estimation is small but oscillating because due to the fact that we have the measurement noise. And in the figure 50, 85, 86, 87, and 88, we can see that the measured estimate that and the real value of the state of the system. And we can see that even under the measurement noise, the estimated value of the state still checks the real value well. And one interesting thing that when we make the simulation is that if we keep the measurement noise and we don't use the LPV unknown input observer, so the controller cannot control the quadcopter well to follow the desired trajectory, or even we lost the control. So now we are going to to conclude. So in this thesis, we propose a new approach for cellular decomposition by introducing the extension of critical point. This extension led to a decrease of the number of cells after decomposition. The result shows that this new cellular decomposition works well even with several concave obstacles inside the environment. And we have proposed a method for maximizing the percentage coverage, and the percentage coverage is up to 97.9%. And then by using the genetic algorithm with some modification on the sharp flip and slide operation, and the TSP problem with additional constraint, we can generate the shortest path for changing the cell of the environment. So for pesticide spraying, we have proposed a method for generating a trajectory with which allows the UV to put the medicine to the entire pest-ridden area of an agriculture area. First, the pest-ridden area have been divided into several small areas we call cluster by using clustering techniques. And after that, each cluster is divided again into several obstacle-free convex polygons. Then this burst trajectory is generated in each obstacle-free convex polygon. And finally, we find the shortest trajectory for changing between the cells, which have using the algorithm that we have already developed in the first section. And for the control case, that if the state of the UV can be measured or estimated, so we develop an LPV H infinity state feedback controller for the mass varying quadcopter. And when the state might not be available, the LPV dynamic output feedback controller and the LPV static output feedback controller are developed for the mass varying quadcopter. And we also proposed the LPV unknown input observer for the mass varying quadcopter. And we can see that this controller and unknown input observer work pretty well for all the cases for seven kind of reference and seven kind of disturbances. And during the thesis, some publications have been published, like in this slide, and some will be submitted. And this is the end of the presentation. Thank you.
Yeah, thank you very much. Thank you, Pham, for this presentation. And thank you also for respecting the time. I just would like to say specific word concerning. I would like to thank you for giving some words about Yasmina, our colleague. I would like to join you in this thought for Yasmina, and I know she did big work in the lab, and
Yes.
as you said, it was also very important for you. So thank you again. Now I think that we have time for a couple of questions from the member of the jury, and let us start with Benoit Marx.
Yes, please.
Benoit, are you ready to start?
Yes, I am.
Okay. Thank you.
Thank you, Mr. President, for introducing and also for mentioning the work and the implication of Yasmina. Yes. First of all, I would like to thank Said and Dalil for inviting me to this thesis, and also inviting me to review this thesis. And thank you, Pham, for this presentation, and also for your manuscript. I found it very interesting and also very well written. In fact, I was of course more interested in the control part, but I also have some question on the past planning, and I was happy to get some new information and to have some knowledge in this.
Yes.
So first of okay.
Benoit, we cannot hear you. I don't know what happens.
Oh, he's out, Professor.
Oui, vous
he's
m'entendez?
trying to... Yeah. Oui, on t'entend, Benoit.
Okay. So yes, I was saying that I was happy to see that in the beginning of your manuscript, the goals and the object of the study was very clearly motivated, and it was a nice thing to read that. In fact, I have some question on the past planning part.
Yes.
The slide 27 to begin with.
Yes.
If it's possible to go to this. In fact, as I mentioned in your manuscript, there's the algorithm that you propose seems to be rotated of pi.
Yes.
Half pi.
Yes, exactly.
Is
it is
it
rotated. Yes, Professor. In fact,
and
yes.
is there a reason for this?
Yes, in fact it is rotated 90-degree, but in fact in the approach we can use the swept line from the left to the right, or from the top to bottom, or the bottom to the top. It depends on what we choose, and to write the code in MATLAB. So so when I wrote the code in MATLAB, I use the approach from the from the button to from the top to the button. So so it is not the compromise, not the synchronized between the definition and the code. I'm so sorry for that, but I think the results are the same. We just change the approach to swap the line from the left to the right, or from the top to the button.
Okay, I thought you tested both of them then and choose the best one.
Yes.
Also in the cell decomposition.
Yes.
So the algorithm, and claim that the number of cells that is obtained is decreased. Is there a proof for this, or is there?
In fact, there is. It's not really the proof, but in fact, I made several simulations for this one. For example, for this really complicated environment like this one. So in our approach, I got only 6 cells, but when I tried with their approach, I got about maybe more than 20, and their approach cannot apply with the non the non-polygon shape, like here in So for my approach, I mean, we can apply also the shape, every kind of shape, not only the polygons.
Okay, thank you. It's only a detail, but I was wondering on the slide 47.
Slide 47.
When you present.
Yes.
47, yes.
Yes.
When you presented the way to.
You mean about
the path generation inside the cell?
About the polygon with the two parallel slides? No.
Yes. Yes.
47,
Yes.
right?
47, yes.
Yes.
47.
I don't know why my camera is really slowly to move the slides. I'm sorry.
No, it's okay.
Yes, this one.
Yes, just the next one. Yes. On the right part, I was wondering why the UAV goes to the border on the B figure.
You mean this one, right?
Because you.
Yes. In fact, no. This is not in the border because I marked this one to easier for to see. So it is in the border, but in fact it is not in the border. Like in this one, Professor. Just this point is border, but this point is not in the border. So I mark it a circle, the big circle, so we can see that it seems in the border. I think this one is not in the border, but this one I think in the border, but this one is not. I think.
No, not on the up and down part of the figure, but on the left and the right.
So yes, so you can see in this one, in this one. So this point should lies in the border, in order to cover the entire area of the polygon. But this point is no. This point is lies inside the polygon. So it depends on the shape of the polygons, and it depends on the also the I think this one we have a very sharp angle. So this one should lie inside the polygon.
Yes, but I was wondering on the next slide because there is a radius r, so you are not obliged, you are not forced to go
because
till the border of one.
Yes, so here we because this point should be here because we have to cover also this part. Yes, and this one we have to cover also this point. So it should be here.
Not this one. No, I'm not talking about S or E. I'm talking about the extremity of the here. Yes.
Yes. So
why are you going?
Yes. So I think this one is in the border. Is right. This one is right, but this one is not because when I plot it, the plot is huge. So.
Okay. No, it's only a detail, but I was okay. On the next slide,
yes.
48. The algorithm that you presented to minimize 48. So
yes,
you presented. It's an algorithm to minimize the to maximize it.
Yes, to detect the angle to minimize the path length, Professor.
Yeah, but the max. I think this algorithm is made for it's the max length is updated when path length is over the max length. So it seems to me that it's a maximum. It's a max, but once again, it's just a detail.
Yeah. So I think So this one, I think this one should be this one should be bigger. Max length should be bigger than path length. So we can update it.
Yes, and it
Yes.
yes, and it should be
Yes.
initialized to plus infinity instead of 0. Okay. So if I have enough time for some more question, I would like to move to the control part.
Yes, please.
Okay. In the slide 86, 89, which correspond to the section 5.5 of the control part, the system that with a known input is split into two subsystems, one with
Yes.
UI and one with only known inputs. And then the known input observer equation, the output of one of the subsystem is provided to the observer. So my question is, how can you compute the output of one subsystem since you only know the output of the system but not the output of each subsystem?
In fact, in my simulation, I use directly signal from the simulation. But I think in the real application, we can use some kind of exact differentiator in order to get to filter the output first before put it to the LPV unknown input observer.
Yes, but the output of the system, but in the slide 89, I guess, if I remember right.
Yes.
The output of the subsystem is provided to the observer. Yes, here in the equation 61. YZ, the last term is considered as
YZ?
Yes, this one, yes.
Yes, so the YZ is the signal that we don't have the output of the system, that we don't have the input.
Yeah.
Yes. So
but it's not the output of the system. It's the output of a subsystem. So it's quite virtual, in fact. So how can you, from the output of the system, which is the only thing that you measure, how can you split the output of the system, which is a real measure, into two different outputs?
In fact, in the real application, we can use the exact differentiator in order to filter the output from it, from the output in order to get the YZ, I think. But in my simulation, I got it directly from, because I run in the simulation, I run the two system parallel, so I will get the YZ directly from the simulation. But in the real application, we can't. I think we can't use the sliding mode differentiator or the exact differentiator in order to get this signal.
Okay. And maybe last question. I found the fifth chapter, which is about control and estimation, very interesting, and realized that a lot of work was done. But I still have 3 questions or regret that, in fact, all the estimation results are given in the case of complete state knowledge, meaning that y is always equal to x. The output is the whole state. Have you tested some other scenarios where only a part of the state is measured? Because in terms of state estimation, in fact, the whole state measurement is a very specific case.
In fact, I think I didn't try it because I mean, your question is for the LPV unknown input observer or for the state feedback controller, Professor?
For all the observers that you have designed and use in your thesis, the output is always the whole state. We always have y equal to x. And it's
yes,
a very specific case.
Yes, for the state feedback,
in
I use
estimation.
the y is the full state. Yes.
Yes,
But
for state feedback, it's obvious, but also for estimation, also for state estimation, you always assume that the whole state is measured.
Yes, yes, I think I assume that the whole state is estimated or measured, and then we use the observer in order to correct the if the signal is noisy, so we can use the observer in order to filter that signal, because as in the simulation result of the LPV annual input observer, I think this is the second simulation. Okay, let me go there.
I don't know what happens, but we cannot hear you correctly.
Professor, can you hear me?
Yes,
Benoît?
yes.
Ah, ok, now.
Oui. Oh, je disais rien, donc pour une fois. C'est pour ça.
Yes, because I'm trying to move the slide, so I don't talk. I'm sorry.
No,
Okay, so I mean in these simulations, so this is we can see there is the white noise inside the white noise that we put in to the output of the system, and I tried with the simulation that. Okay, let me go back to the diagram. This one. So this one I use I design the LPV unknown input observer, and I use the state feedback that we developed in the previous subsection. And one interesting thing that if I put some measurement noise and I don't use the LPV unknown input observer, I put directly this signal to the state feedback controller. So the quality of the control is really bad, and even the control is lost. But when I put the signal through the LPV unknown input observer, I got very good result, like in the figures that I have already shown you, like in this figures. Yes.
Okay.
So do you have any more questions, Professor?
No. Benoît?
No,
Did you finish?
No. Yes. And as I just would like to last remark, and I want to congratulate you for all this amount of simulation, because in many theses the examples are very simple and unrealistic, but in your thesis you really made a huge effort to give many simulations that are realistic, and I found it's a very good point. So thank you for your presentation and all your answers.
Thank you very much, Professor, for your reviewing and for your kindly to be here to the jury member. Thank you very much.
Okay, thank you, Benoît. Thank you, Benoît, for these questions and for the response given by Pham. And now let's move to the second reviewer, Pedro.
Oui.
Can you hear me?
Yes.
Okay,
yes.
so you can start the questions.
Okay, thank
Hello,
you, Mr.
Professor Pedro.
Yes, sorry?
No, I just want
to say hello
to say hello to you.
Say hello, Mr. Pham. So first of all, thank you, Said and Dalit, for inviting me in this PhD thesis, and thank you, Mr. Pham, for this presentation, for this clear presentation, and for the time and the slide presented here and the result presented here in your work. So I have some questions. My questions are more related with your main part, that this is the path planning, the coverage path planning and the controller. So for the path planning, so you are presenting some result here, and but I'm not sure that it is necessary, or that it could be improved. For example, my question is, do you consider that it could be necessary to consider the dynamics of the vehicle, of the aerial vehicle, for covering your problem, because I think that in your problem you are not taking into account this. You are only trying to coverage to make the path planning. Do you think that if you take into account some restrictions or some constraints about the dynamics, it could be improved your results?
Yes, Professor. In fact, I have already researched something about this one, and the dynamic constraint for the path planning for UV will be in my future paper that we are working on it now, because in the context of this thesis we don't consider any dynamic constraint like speed or the speed or the accelerations or even the dynamics obstacles. But in the next of our paper, we will consider all some of the dynamics constraints.
And do you consider that the result could be improved, or the result could be worse?
I'm not sure about that, because I have already developed something, and I can see also the speed in order to it's the speed. For example, okay, let me move to the pathway path, and we will see some figures, so I can better explain you. Okay, so okay, this one. Okay, so I have already worked something about this one. So I consider that the UV has to flow from N to M. But I mean the UV. But I mean we have the radius of the of the spreading pesticide. So, in the reality, the UV cannot follow exactly from N to M in this line. So I consider that it can be oscillate, as for example in some part of this one, and I have to design I have to take into account the dynamics the dynamics constraints like the speed, the acceleration, in order to guarantee that the quadcopter should lies in only in I call the corridor near this lines. I have to generate the some kind of the way with this line as at the center, and the quadcopter with the dynamic constraint of the speed and the acceleration cannot get out of this corridor. So I think it will be more interesting to develop.
Okay. Okay, thank you. So in the yes, in this part also, in this part planning, you are presenting two algorithms, two different algorithms, one for the infected area detection and another for the
Yes.
pesticide spraying. So why it is possible to propose only one solution, or why two solutions? There are several, there are different both algorithms, or why do you propose, or is possible to propose only a general solution or a general methodology for covering it?
You mean this the differentiation between these two, right?
Yes.
Okay, so in fact, I have to propose these two method because so you can see in this in the first case, so we can see that I mean this in this case the area of the coverage regions will be much more than this than in this case. So if we use the UV to spread the pesticide in on over this one, so we will lose more the medicine in these regions than in this region because the area of this region in the second case is less. However, one another thing we have to take into account that maybe if in this case we have more convex polygons, more convex smaller polygons than in this case, so the trajectory for the UV to follow and to cover on this path might bigger than this in this case because we have less convex polygons than this one. So I have to consider these two cases in order to compare the which one is better. So there is the compromise between the amount of medicine and the trajectory length. It means that the working time or the energy consumption. So we have to take into account this on two cases.
Okay, thank you. So can you go to the slide 27, please?
Yes.
It's 27.
Yes.
Yes. Yes. So in this part, you are working with cellular decompositions.
Yes.
And so in this part is the number of the cell varying with respect to the obstacles and with the form of the obstacles, or is completely different?
I'm sorry, Professor, I cannot hear you clearly. Can you repeat the questions?
Yes, for example, here you can see that you have six, for example, 6 cells.
Yes.
After the compositions.
Yes.
So this number of cells depends of the number of the obstacles and the form of the obstacles, or only it is the methodology that you are proposing?
In fact, the number of cells depends a lot of the shape of the obstacles and their positions. For example, if we rotate these obstacles and we put it to another place, I think the number of cells we get after this cellular decomposition will be different, not 6 like the previous thing. And
Okay.
the more complicated obstacles we have, for example, we have more concave obstacles, so the more cells will be.
Okay, so
Yes.
could you go to the slide 51, please?
Yes. Uh, 51, right?
I think that is 51, but maybe it's not 51. I think that maybe could you go to the 50?
Yes, this one.
Or maybe yes, maybe I don't remember. So and in the part when you are computing your for the covering the area, my question is: are you computing the time to cover the area? Are you computing how many times did you take for it? And my second question is: are you considering or are you estimating the time that the drone cover it?
In fact, in my simulation, I don't calculate the time for the UV to follow. I only calculate the trajectory path length to cover or on this infected area. However, I think the trajectory path length somehow related to the time of the working time, because maybe there is no direct function between them, but somehow I think there is the relation between the working time and the trajectory path length for the UV to follow.
Okay, okay. So I have two last question if I can. So is more related with the controller. This is for the slide 53 or yeah, 33 or 55. So this is the part that I'm a little surprised, because in your controller you have different kind of controllers. You have an integral backstepping for the altitude. You have also for the position a PD controller.
Yes.
And represent 2 or 3 controllers for the attitude. So why are you choosing this kind of controllers? Is for robustness, for precision, or why are you decomposing the controller of the vehicle in 3 parts?
Yeah, because I mean, yes, in fact, when I designed this controller, it might be 3 years ago for the LPBS conference. So at that time, so I developed this controller, and I found that this controller can make the simulation runs pretty well. So I choose them. So I mean, there is no special reason for choosing these three subcontrollers together to form the controller.
So because you are proving here your results in simulation, but do you consider that using 3 kinds of controllers is different, but because they are different, the controller? So do you consider that for real time it is I don't know, it is you will have the robustness that you want? Because you need to connect the attitude controller with the altitude controller.
In fact,
if you go please to the slide 25.
yes.
No, sorry, 55.
Yes,
Sorry,
55.
sorry, yes.
Yes,
So
well,
I think that yes, in this slide you can see that you are computing the second derivative. You are computing different derivatives, and that when you are applying these variables or these parameters, if these measures are noisy, so you will also increase the noise.
yes.
I just a question about the controller, but if you consider that the controller is robust, it's okay for me. My last question is more related with your simulations.
Yes.
If you can go to the slide 69, please.
Yes, 69. Yes. Yes, this one, Professor.
Yeah. Okay. So yeah. So when you propose or when you validate your result or the controller, we can see here, for example, in figure 61, that you are making a square. But
Yes.
my question is, are you validate the controller with respect also the path planning that you are proposing in section in chapter 3, I think.
In fact, I didn't do it because in fact I don't have enough time to do a lot of thing, and yeah, no, I didn't apply it to my territories that I have already graduated in the path planning path. I'm so sorry for that.
Okay, so no more question. Thank you very much, Mr. Pham, for this presentation and for clarifying some of my questions. Thank you.
Thank you very much, Professor.
Thank you, Mr. President.
Thank you. Thank you for these questions. So now let's move to the examiner. And we start with Professor Christina Manu from Central Supélec. So Christina, could you please go ahead?
Thank you very much, Mr. President. I'd like first to thank Saeed and Dalil for inviting me to this committee. I'd like to congratulate Mr. Pham for the very nice presentation that we had today, a very pedagogical presentation. I really appreciated also the manuscript. It's very interesting the way how you presented all these UAVs simulations and all the recap tables that you put on all the existing UAVs for the applications related to precision agriculture. I think I will give take a manuscript and give it to my students, to all my students, in the course involving drones to read at least the first part, and then to try to understand some of the control laws that you proposed. So I was impressed of the number of control laws that you propose and you compare. It's very, very nice. Of course, I have also some questions, and I will start with a question related to the slide 43.
Yes.
So it's one of the slides. Everybody asked question on this. So 43.
Yes, this one, Professor.
Exactly, perfect. So here you have two methods. One for the minimum convex and polygon, and one for the boundary polygon. So what you call the minimum convex polygon, it's the convex hull. Is that right?
Yes, it is. This is the convex hull, Professor.
Okay, that's good. That's good. So I am wondering something. When you develop, actually, when you propose these polygons, and you don't take into account any considerations about the wind direction, you just did this part offline, and you consider don't consider the effect of possible wind or other perturbations. You consider, for instance, that these perturbations will be attenuated by your observers and controller. But do you think it will be interesting to see how the effect of the wind direction and other disturbances could influence on the energy consumption and could change, let's say, the way that you the way of the path that you'll use in these polygons?
Yes, Professor, because in fact this is the I mentioned in the perspective. In fact, this one is really complicated because when we have the wind, so we have to take into account also the collision. There might be the collision between the quadcopter and the obstacles. So we have to recalculate the trajectory under the wind condition. So in fact, for that case, we have to measure even the speed and the direction of the wind, and then from the wind, from that information, we will recalculate the trajectory based on the wind information and the coordinate of the obstacles. So these things this question, your question is really beautiful. But this one will be my future work, professor, not in this thesis. I am so sorry.
No, don't worry. It was just an idea. Okay, it's interesting. So you were thinking about this, so that's very good. One question is also related to this path that you consider, which is more like a collection, let's say, of segments. I was wondering why not having some one path which is more smoother, let's say, which is something like more similar to a sinusoidal form, or when you are inside this boundary.
I'm sorry, professor, I cannot hear you well. Can you repeat the question, please?
Yes, of course. So when you have chosen the path to follow inside this the minimum convex polygon or the boundary polygon, okay? So you have a given path to consider. And this path is mainly composed by several segments.
Yes.
Line segments.
Yes.
Okay. And I was wondering, and you had the same result actually in your manuscript issued from the in artificial intelligence result, let's say. And I was thinking, why not having a path which was smoother, something like more closer to a sinusoidal?
So this trajectory is only the waypoint, professor, and from that waypoint, I mean the waypoint is some kind just the trajectory that we have some waypoint for the UV to follow, but from one point to another point, there is I think there is a different problem of the control, because we have to control the UV to follow from the point A to point B. So that's why I have already explained to Professor Bonomax that I have already thought about the problem that we will generate some kind of corridor for okay, let me go to that one. So for example, for the UV to follow from the N to M. So if we want the UV to follow exactly in this lines, so I think it's really hard to follow exactly, because the UV might oscillate some, and so I was thinking about the problem that we generate some kind of corridors, and the UV has to always inside that corridor, and it goes exactly from the point N and goes inside the corridor to exactly point M. So we can ensure that that when the UVs flow inside this corridor from point N to point M, so and also to the point M, the whole area of this polygon will be covered by the quadcopter. So this is also the so we have to add some more dynamics constraint about the velocities, about the accelerations, and also maybe about the power consumptions, and about the real dynamics actuator of the quadcopter, in order to follow this path inside the corridor that we defined.
Okay, thank you so much. Can we pass now to the slide 59, please?
Yes, Professor.
So actually, in the slide 59, you have several varying parameters.
Yes.
And yeah, we'll just wait a little bit just to have the parameters to see them.
Yes, so here we have 3 varying parameter, Professor.
Exactly. And my question is the following one. I was wondering, what are the parameters which are the most influent on the output? Let's say, if you have some uncertainties on some of these parameters, what will be the most influence on the uncertainty of the output of the system? Let's say, which of these parameters is the most influent? So you can consider, let's say, 5% variation for one parameter, 20% for one parameter, and your controller will still be good.
You mean that we have to define the some kind of the uncertainty for each parameter, right?
Yeah, I was just wondering if you had some robustness analysis and if you just did some test or just check which of these parameters is most influent.
No,
which can be.
No, I didn't
Okay.
do it because I mean for this varying parameter, I just put them inside the interval from the minimum to maximum, and then I will generate the polytopic form from this this interval. So in fact here we have 2 power 3 equal to 8 vertices. So but I mean for your question, I didn't put any I mean this some kind of an exact parameter. So I think if we have an exact parameter.
Okay. You almost answered my question. You told me that you put some bounds on your parameters.
Yes, some bound. Yes.
Do you remember for these bounds that you have also the nominal parameter with plus minus this bound, this delta, this variation. So do you remember this variation? How much it was? 5% that you consider, 10%? Just like this, if you remember.
Oh, I'm sorry.
Don't.
Because, no, I'm sorry. I don't. I cannot remember this.
No, there's no problem.
Yes.
That's no problem. So you will open later on MATLAB and you'll check on your simulation.
Yes.
I was just curious about the influence. Okay. Another question also related to the perspectives of your work. So in the manuscript, you said that you are also interested to propose an observer in order to estimate online the quadrotor mass and the moments of inertia.
Yes.
Do you have already an idea what is the kind of the observer that you think you will use, or?
No, I haven't thought about that. But I mean, I read some paper. I think it's a paper of Professor Kumar in the United States, and he and his group has already developed one method in order to, and I think they use the extended Kalman filter in order to estimate the mass and the moments of inertia online when the quadcopter is flying. So I think we can, based on their work, in order to improve some kind of observer or maybe I mean a filter in order to get that values online with the cheap sensors such as accelerometer or gyroscope.
Okay, thank you. I also appreciated in your presentation and also in your manuscript all the convergence proof based on LMIs, and for me that part was very clear. So I don't have questions on this part. I will just add a very last question for your defense from my part. And at the beginning of your thesis, you showed a lot of UAVs. Okay,
Yes.
and you have this nice application in precision agriculture, and I see that in the perspectives is that you want to implement your result on a real drone. So, what is your ideal drone, on which UAV you will like to implement your results?
Yes.
What kind?
Yes. In fact, I mean, when during my thesis time, in fact, Professor Said Mama and Professor Yasmina gave me, I mean, bought me some equipment for me to assemble the ruined quadcopter. But I mean, due to many reasons, I couldn't make it fly. But I mean, now I am concerning about another type of unmanned aerial. So that I mean, it contains also the four rotors in order to have the ability to vertical takeoff and landing, and it also has the fixed wing in order to fly in the plane, and maybe the combination of these two type of aerial vehicles, quadcopter and the fixed wing could be very interesting for the UV to be applied in precision agriculture, because it has all the ability of these two type of UVs. It has the ability to take off, landing vertically, and it can fly very fast, and yes, and etc. So I think my future research should be on that fixed type of UVs, quadcopter and fixed wing.
Thank you so much. I'm happy with your answers. I have no questions now. I will just let the Mr. President to continue. Thank you.
Thank you very much,
Okay.
Professor Christina Manning.
Thank you, Christina, for these questions. And before giving the possibility to your supervisor to tell some words about your work, let me ask you some questions. So I prepared around 10 questions, but unfortunately, all of them were already given by my colleague, in particular Max, Benoit, Marx, and also Christina, in particular concerning the map division. And I was satisfied by your response. So I will ask you another question. Just one remark. The first is not really a question. It's just a remark, because you, in your work, you try to develop observer, non-observer, but I did not see any study of observability of your system.
Yes. So yes, in my thesis, I didn't. I didn't take into account the observability of the system.
But how you can develop an observer, since you did not verify if the system is or the observability is verified or not?
Maybe I was lucky when I developed it, and I think the system is observability, but I didn't prove it. So but I mean for the research.
Yes, I know. Don't worry. The system is observable, but I think it's for the quality of the work. I think that you need at least make a remark that due to the particular form or something like that, to at least one remark, or to say that the observability is verified. Otherwise, if you go directly to the development of the design of the observer without checking the observability, it doesn't make sense. You know what I mean?
Yes, yes, I understand. Thank you, Professor. I went write something more in before the developing of the
Yes.
in the thesis.
I have another remark. It's not. I don't remember exactly which slide, but it looks like that you have the singularity of your in your controller, but you did not speak the way that you can overcome, and you can overcome this singularity. I don't remember which slide, maybe the one before or after, where you have singularity in which you have cos theta and sinus theta. Maybe one of them can be equal to 0. So this could be a singularity, how you can develop a controller without taking into account this.
Oh, so I think we should make some
equation,
assumptions.
56 maybe, 56 or 57, or slide 56 or 7. Okay. No, 50. Okay. No, not here. 50. No. Oh yeah, maybe here. U1 is equal. So here you can have a problem of singularity. Is it? No, not this one. Please, 57.
Yes.
57. Yes, the next
mean
one.
Here, right?
Yes, here.
Yes.
Are you sure that psi and theta is not equal to 0? Cos theta and cos psi are not equal to 0?
No, because so the angle will be pi over 2. So it's impossible for the quadcopter to rotate.
So I don't remember. Yes. So this is why I would like to see exactly, because I did not see. Maybe you shown it, but I did not see the theta and psi in your presentation. I don't remember exactly where.
Yes.
Otherwise, you need to. So suppose that you have singularity. Do you have an idea how you can use the controller?
In fact, I think there's one popular solution that they have already widely used, is that we use the I don't remember the name, but it converts the state of the quadcopter from 12 to I think how to call it, it's because in they don't use the I don't really remember his name, but there is one method so that they transform the state into another kind of state, and there is no singularity. I don't really remember.
No, the singularity is it cannot be modified by using transformation, because it's structural properties. So you cannot remove the singularity. What you can do is just to make a controller with switching around this singularity. It means that you can have a switching controller around this singularity. So this is the way that we can overcome the difficulty due to this singularity. Okay. Do you think that you can, because the quality of the image that you will take with your drone will depend on the stability of your drone? I mean that you must be in a stationary position. That's right?
Yes. In fact,
yes.
I think it doesn't really depends on the stability of the control of the quadcopter, because I mean when we want to attach the camera to the quadcopter, we have some kind of special equipment in order to stabilize the camera with.
Okay.
So I think if we have that kind of stabilization equipment, we can stabilize the camera. And you can see some videos that they took from the UV. I mean the video is very stable even with the wind, high wind. Yes.
Yes, I know that when considering the quadrotor and the drone, sometimes we have problem of perturbation. I mean regular perturbation, not noise. Regular perturbation due to the fact that you have vibration of the pallet. You know, So how you can take into account this vibration?
So I think this
Because
vibration,
yeah.
can we can consider as some kind of unknown input unknown input, and maybe we can develop an algorithm in order to estimate it, and
Yeah.
and put it. I mean, when we can estimate it, we can put it to the controller in order to make it smaller effect to the quadcopter.
Are you sure that you will be able to estimate this vibration?
I'm not sure, because we need some kind of algorithm in order to model it, and I'm not sure that we can do it, but I think there is another method that we can assume that this vibration is lies in some interval, and then we will
Okay.
design the controller in order to in order to in order to react. I mean, the less effect from that vibration inside the bound that we have already bounded to the
Yeah.
quadcopter.
Okay. So I think that you can see the work of John Hauser. He developed a very interesting solution for the pivotal planar vertical takeoff and landing, which can be easily applied to your case in case of regular perturbation, and the way that he take into account this perturbation, and you can do it. And he also proposed, because you did not explain the way that you make the implementation in real case of your system, of your solution. So you can maybe find a good idea about the way to how you can implement your solution. So do you have an idea about this solution when you make the real implementation for the system?
Till now, I don't have any idea, yes, professor, because the practical work is really annoying and takes a lot of time and experiences and some tests. So I think at the time that I'm working with the experiments, I think some ideas will comes to me, and at that time I have to resolve it. But for now, I think no.
So I think if you can, sorry. I think if you can make experimentation for the next step, it will be a real and good contribution, because your work is very interesting, as well as the application that you propose in agriculture. So this is why I think that it could be a good things that you will do it. Okay, so I've seen, I don't remember which which slide, but I've seen also in the document that you sent in figure 5.14, so that you are using derivation of the input.
Yes, you mean about the unknown input observer, right?
Yes, exactly.
Yes.
That you are using, and this is a little bit not good solution. I mean, what happens if your in your input you have perturbation, impulsive perturbation?
You mean when I
Yeah.
explained about when? Okay, let me go to.
Yes. So how you can deal with? I mean, if you have a perturbation, you can use a filter, for example. But when you have impulsive perturbation, you know that the derivation of the impulsive is you cannot calculate it. So how you ensure the stability of your observer in this case?
So in fact, at that case, we have to assume that our distribution lies in some bound, and we have to design
Okay.
the controller and observer so that when the distribution is at bound, we can guarantee the stability of the system.
Okay. So let me give you last questions. Your work is very interesting, because you are dealing with a problem in agriculture, but I think that one drone or one quadrotor will not be sufficient. So do you think that if we apply fleet of drone or fleet of quadrotor, you can be able to apply your approach for fleet of drone?
Yes, Professor.
And how you can imagine to develop this solution? Because you will have problem. Yeah.
Yes,
Sorry?
in fact, we have to. I mean, the future work might be the combination of the UV team. So, for example,
Yes.
and maybe this UV have to connect it to one main server, and the main server will know I mean to which UV will do what, and which work part has done, and we have to design another software in order to control on the UV. For example, if one UV run out of energy, or something happened to that UV, so the main software has to recalculate the work for the others UV to accomplish the whole work for the ones that have already dead. So this is, I think, it's very interesting approach for the UV teams.
Okay, so it means that what you are proposing is a problem with multi-agent systems.
Yes,
the approach
exactly,
of
Professor.
multi-agent systems, and you are proposing the problem of, because you will have problem of collaboration and communication. So you have collaboration between drone and communication, because they have to communicate.
Yes.
Is it true or not?
Yes. So, we have to communicate between the UVs, and even between the UV
yes.
to the center.
So,
I mean, to the main center.
Okay, so you are proposing the approach, decentralized approach.
Yes.
Or centralized approach. Which one you are thinking about? Which approach you are thinking about when you are speaking about multi-agent systems?
So we will have one we call maybe the main server, and that main server will control everything, and every UV has to connect and send the information to the center, and
okay, so you are proposing centralized solution.
Yes.
Okay, so on the main agent, so there is no the main agent will send information to all drone.
Yes, and even even the main software will recalculate the trajectory for the UVs to follow in real time.
Okay. Yes. Okay. Thank you.
Thank you very much.
I finished with my questions. I have other questions, but just the remarks we can discuss later after the thesis. And now I have to move to your supervisor. I don't know, maybe I can start with Dalil.
Okay, thank you, Mr. President. First of all, I would like to thank all the members of the jury, the reviewers, the examiners, and the president for all the questions, discussions, and the careful reading of the manuscript, and all the points that discussed today. I would like to thank also Said Mamar for giving me the opportunity to supervise this thesis. As you know, this thesis has started in 2016 with Professor Yasmina Bestawi and Professor Said Mamar. Unfortunately, Yasmina Bestawi passed away in 2018. So Said Mamar proposed me to supervise with him the rest of the thesis. Notice that a great work and a lot of a great part of the work of Tihang is done with the supervision of Yasmina Bestawi. My supervision is in continuation with the work done with Yasmina Bestawi. So about Tihang, Tihang is one of the most motivated students that I have had to supervise. He's always in doing research, asking questions at any moment, doing simulations about drones, about a lot of things. I think he always wants to learn new things. We can see this in the manuscript with a lot of kind of controllers, observers, and another part which is not in the manuscript is the practical part. In the work, some work is not in the manuscript, especially the Tihang spent a lot of time in constructing the quadcopter in order to validate all the simulations, all the controllers, observers, and the path planning techniques. Unfortunately, due to the pandemic situation, we could not do those validations, but I hope that we can perform them in the near future. For all these reasons, and for the human and scientific qualities of Tihang, I want to say thank you for the opportunity that you have given to me to work with you. And merci beaucoup et bon courage pour la suite. Merci,
Merci beaucoup,
Monsieur le
professeur.
Président.
Merci beaucoup.
Merci. Mr. President.
Merci, Dalil. Thank you. Thank you very much. Now we finish with Professor Said Mangan. Said. Said, we cannot hear you. Ah, Said nous a quittés.
Il va se reconnecter. Il est en train de...
Oui.
Oui, Said.
Ah oui, pardon. Oui.
Ouais.
Écoutez, je vais parler en français parce que finalement, Tihang, quand même, en 4 ans, a bien appris le français, même s'il le cache un petit peu. Écoutez, je vous remercie déjà. Je tiens à remercier l'ensemble des membres du jury d'avoir bien voulu participer donc à l'évaluation de ces travaux de thèse. Une mention un peu particulière pour Benoît et Pedro pour leur rapport, et puis aussi pour Benoît parce qu'il a accompagné cette thèse-là durant son déroulement dans le cadre des comités de suivi. Il a déjà pu donner de bons conseils à cette époque-là, enfin il y a globalement 2 ans. Bien entendu, je remercie Yasmina d'avoir été à l'initiative de ce travail de thèse. C'est Tihang qui a connu la France, puisque même un de ses enfants est né en France, à Toulouse. Était donc en contact avec Yasmina et ce travail de thèse et cette thèse donc ont émergé à partir de leurs discussions. Et on a eu d'ailleurs une difficulté parce que effectivement c'est un travail de thèse sur 4 ans, initialement prévu sur 4 ans, et puis qui allie à la fois planification, observation et commande. Ce qui est en soi relativement rare parce qu'effectivement il y a beaucoup de choses à faire à la fois sur chacun des 2 domaines séparément. Donc, je tiens vraiment à remercier aussi Dalil d'avoir poursuivi sur cette thèse-là sur les 2 dernières années, d'avoir accompagné, proposé de nombreuses idées. Tihang n'a pas beaucoup parlé de son investissement au niveau du projet européen e-drone. Réellement, ce projet-là qui ambitionne à diffuser les enseignements autour des drones a réellement été porté au sein de l'université par Tihang. C'est des deliverables, c'est des montages de modules d'enseignement, c'est de l'accueil d'enseignants de pays, de pays européens qu'il a formés sur place à Évry. Même si sur son travail de thèse, la partie expérimentale n'est pas complètement aboutie, il les a accueillis, il y a des drones envolés, dans la volière que nous avons ici à Évry. Malheureusement, bon, c'est un petit clin d'œil, malheureusement pour lui, et j'en suis vraiment désolé. Il n'a pas pu beaucoup voyager parce que les problèmes de visa avec les ex-pays de l'Est étaient un peu compliqués. Mais bon, mais quoi qu'il en soit, enfin, il a réellement beaucoup donné sur ce projet européen. Voilà, donc moi, je n'ai pas de questions supplémentaires, hein, si ce n'est de le féliciter pour l'ensemble des travaux qu'il a réalisés, la qualité du travail, ses qualités humaines, hein, sincèrement, c'est un doctorant hors pair. Et au-delà d'être un doctorant, c'est réellement un collègue hors pair. Hors pair parce que sincèrement, enfin, je pense que Dalil me rejoindra sur cet avis-là. On le considère réellement comme un collègue. Voilà. Et j'espère que nous pourrons continuer à travailler ensemble au sein du laboratoire en tant que chercheur membre associé au laboratoire et qui pourra nous rendre visite plusieurs fois et beaucoup de fois, hein, une fois que les choses, que les problématiques sanitaires seront rentrées dans l'ordre. Voilà, donc merci beaucoup Itiang pour ces 4 années, 4 belles années, et puis toutes mes félicitations. Merci Monsieur le Président.
Merci, merci à tous, merci Saïd. Alors, Pham, on va vous quitter pour quelques moments, donc on va switcher sur l'autre salle pour délibérer, puis après on va revenir. Donc, restez connectés, ne vous éloignez pas trop. Voilà, donc on va couper ici. Donc, si vous switchez sur l'autre salle, donc n'oubliez pas de couper le micro de cette salle.
Merci beaucoup, professeur.
Merci.
Très bien.
Au revoir.
Est-ce que tout le monde est là?
Yes, I can hear you.
Oui.
Je suis là, ouais.
Oui, on est là.
Très bien. Très bien. Donc, alors, Pham,
Yes.
okay, you can hear me. So we decide to make the decision in French. Is it okay for you in French or you prefer in English?
Yeah, please in English because my French is really bad, Professor.
Okay. Okay. So let me first of all congratulate you for the presentation, and I would like to let you know that the committee has really appreciate your presentation, the quality of your presentation, the quality of your slides, and the presentation was really very pedagogical way. So you succeed to answer to a couple of questions of all the questions of the member of the jury. There was many questions in different aspect. From practical and theoretical aspects, so you succeed to give satisfaction to all the members of the jury for these questions, and for all these reasons, all the members of the committee, they decide to congratulate you for the quality of your work, and they decide to award you as a doctor in control or automatic, I don't know how to say, control from the University of Paris-Saclay. Congratulations, Pham. You
Thank
are
you very
Dr.
much,
now.
Professor. Yes, thank you very much, Professor. So, can I say some word, Professor?
Sorry?
Can I have some words? Hello, can you hear me, Professor?
Yes, I can hear you. You can go ahead, please.
Yes, in fact, I don't know what to say now, but first of all, I would like to thank you all the jury member, Professor Christina Manu, Professor Pedro Castillo, Professor Mohamed Juma, and Professor Bruno Max for kindly accepted to be the jury member. And I would like to thank my supervisors, Professor Yasmina, of course, Professor Said Mama, and Professor Dalini Chulan. Because I have been waiting for this day for a long time, and today I succeed. So I don't know how to say, but just one phrase. Thank you very, very much for what you have done for me for all the time and during the for the review process and for the jury. Thank you.
Thank you, Tiang.
Thank you.
Thank you, Tiang. Merci.
Thank you.
And congratulations.
Thank you.
Yeah.
Thank you very much.
Okay, so Dalil?
Oui.
Saïd, je vais corriger donc très rapidement et vous envoyer le document, et puis après vous soit vous l'imprimez, soit je vais essayer de le mettre sur le PDF directement.
D'accord.
Très bien.
Pour les autres membres du jury, n'oubliez pas de m'envoyer ou bien d'envoyer directement à Saïd les procurations.
Pas de problème.
C'est dans les documents que vous envoyez.
J'en ai reçu qu'un seul, celui de Christina.
Je t'ai envoyé la mienne aussi.
Je t'ai envoyé la mienne aussi.
Parfait, c'est bon. Merci beaucoup.
Bon, je pense qu'on peut quand même l'applaudir.
Ouais.
Thank you very much, professors.
Thank
you.
Thank you.
Au revoir tout le monde. Congratulations, Mr. Pham.
J'espère qu'on aura l'occasion de faire un bon repas tous ensemble ici à Évry.
Je l'espère aussi. On l'espère tous. À très bientôt. Merci.
Bon courage.
Au revoir.
Merci à tous.
Au revoir, tout le monde.
Merci, au revoir. Merci, au revoir.
Merci, au revoir. Merci à tous. Au revoir.
Merci.